All right, we were talking about strong and weak bases in the last video. So as you can see here, you have a listing of the strong bases on the left side of the slide, and the group 1, group 2A metal hydroxides are the strong bases. All right. Now group 1 hydroxides completely are soluble in water. All right. Now some of the group 2A hydroxides, and magnesium hydroxide is very soluble in water, but others like calcium hydroxide and strontium hydroxide and barium hydroxide have rather low solubility, but when they do dissolve, it's unidirectional, the reaction. That means there's 100% dissociation. All right, so the stuff that does dissolve breaks up into water completely into ions. All right, so hence they're still considered to be strong bases. The weaker bases like ammonia, bleach, or some of the carbonates, bicarbonates, okay, I stand corrected. Magnesium hydroxide actually is a weak base, all right? So it doesn't come under the strong bases, okay? And then you have aluminum hydroxide, which is also a weak base, all right? You can see that the reason that they're weak bases is because of the fact that they do not break up 100% in water, all right? So they do form some hydroxide ions, but not to the extent like the group 1 hydroxides, okay? So like I said, a lot of household cleaners are hydroxides. For example, the drain cleaner is potassium hydroxide, so is oven cleaner. Windex, that's ammonia. Bleach, that's a hypochlorite, sodium hypochlorite. And then you have detergents which have sodium carbonate and phosphate. Toothpaste has baking soda, sodium bicarbonate, and baking powder. And then some of the antacids are hydroxides of magnesium and aluminum and so on. So they are quite useful in terms of they have different uses, mostly in terms of cleaners and so on. Okay, so if you have a strong acid, its corresponding conjugate base is weak. Okay. So when the acid strength increases, as we saw in that table, its conjugate strength base will decrease. But if the acid strength decreases, then its conjugate base strength will increase. Therefore, water, the weakest acid, has got the strongest conjugate base, which is OH minus. All right. So if you look at an acid-base reaction, you'll always have the strong acid and strong base lined up on one side, and then the other side has the weak acid and weak base. All right. So that's how it always works out, whether it's on the left side of the arrow or the right side of the arrow. All right. So it's always strong on one side and weak on the other side. Okay. All right, so this example illustrates that you have sulfuric acid, strong acid, and you have water. So sulfuric acid dissolving into water, reacting with water. Okay. Now, water in this case is acting as a base because sulfuric acid is donating one of its proton to water, and then it forms H3O plus, the hydronium ion. All right. Now, compared to sulfuric acid, the hydronium ion is the weaker of the acids. Okay. If you compare water and the bisulfate ion or the hydrogen sulfate ion, that's going to be H2O is going to be stronger compared to the hydrogen sulfate ion. All right, okay. So you'll have to refer back to table 11.3 and then compare the strengths. All right. Once you've identified one of the species as strong, it just follows logically that if you've identified H2SO4 as strong, then logically strong is going to be on one side, weak on the other side. So H2O has to be a stronger base compared to HSO4 minus. Okay. So the direction of the reaction is always going to be from strong to weak, right? Hence you can see that the direction of the arrow is from left to right. All right, here you have a carbonate ion dissolving into water, and it's grabbing a proton from water, all right, because it forms HCO3 minus, all right. So carbonate ion is grabbing a proton from water, therefore water is the acid. The carbonate is acting as a base. On the other side, you have the hydroxide ion. Now remember, the hydroxide ion is the strongest base. Therefore, if this is the strong base, the HCO3 minus has to be the strong acid. Remember, strong and strong are always going to be on the same side. Therefore, the carbonate ion is going to be the weaker base and water is going to be the weaker acid, right? So the direction in which the reaction will proceed in this case, is going to be from right to left, all right? So the reverse reaction will predominate, okay? All right, so in the study check, it says identify each of the following as a strong or a weak acid. Okay, HBr, strong acid. HNO2 is not among the listed strong acid, so this is a weak acid. NaOH is a strong base, group 1 hydroxide. H2SO4, strong acid, okay? CuOH2, it's not a group 1 or group 2 hydroxide, so therefore it's weak, all right? So strong, weak, strong, strong, and weak. Okay, using table 11.3, identify the stronger acid in each pair, okay? So you have HNO2 or H2S. Okay, so they're both weak acids, so you'll have to look at where they're placed, all right? H2S, hydrosulfuric acid, is kind of midway here among the list of the weak acids. And then HNO2, nitrous acid, is higher than that, all right? Therefore, HNO2 is the stronger acid. Okay, and then you have the bicarbonate ion or an HBr. That's a no-brainer because HBr, hydrobromic acid, is a very strong acid. Then you have H3PO4 or H3O+, the hydronium ion. Now, hydronium ion is the last among the strong acids, but H3PO4, phosphoric acid, is a weak acid, all right? So H3O+ is the stronger acid. Okay, section 11.4. Here we are going to be looking at equilibrium constants with respect to the dissociation of acids and bases, all right? We cannot have an equilibrium constant for a strong acid because it goes to completion. Similarly, a strong base, there's no equilibrium because it goes to completion. It's a single arrow. When you have a double arrow, that means an equilibrium is being established, and therefore you can then calculate an equilibrium constant. all right? So the equilibrium constant in this case is called Ka, not Kc, but Ka, all right? Lowercase a means acid. Or if it's a base, it's going to be called Kb, all right? So lowercase b signifying a base, okay? All right, so here you have formic acid, HCHO2, dissolving in water, forming H3O plus and CHO2 minus, the formate ion, okay? So this is an equilibrium here, and when you write the Ka expression, it's going to be products over reactants. And remember, you cannot include liquids or solids in the equilibrium expression. So it's going to be H3O plus times the CHO2 minus divided by the HCO2 concentration, okay? Okay, so you can only calibrate or write the equilibrium expression if you have a weak acid, okay? So the concentration of the H3O plus times the concentration of the formate ion divided by the concentration of the formic acid, and that's the acid equilibrium constant, or Ka, for formic acid. Okay, so you see that? Products over reactants. So H3O plus times the formate ion concentration divided by the concentration of the formic acid. And then that has been found to be 1.8 times 10 power negative 4. All right. Again, these are standard numbers that they usually determine by experimentation. Okay. And usually at a standard temperature like 25 degrees centigrade, right? So for formic acid, the acid dissociation constant is 1.8 times 10 power negative 4. Okay, if that number is small, okay, like 1.8 times 10 power negative 4, less than 1, that means its acid is not breaking up too much, all right? So the equilibrium is favoring the left side, the reactants, okay? If it is really large, greater than 1, then of course the equilibrium is favoring the right side. That means the more of the acid is breaking up, okay? So really weak acids have very small Ka values, whereas the stronger among the weaker acids have larger Ka values, okay? Similarly, you can write a base dissociation constant, a Kb expression, okay? So here you have methylamine, an organic base, dissolving in water, forming CH3NH3 plus. Okay, one of the protons comes off, latches on here, and the hydroxide ion. So products over reactants, so CH3NH3 plus times OH minus divided by the CH3NH2, that's Kb. And again, that was experimentally found out to be 4.4 times 10 power negative 4. So the same principle. If it is really, really small, that means it favors reactants. If the Kb value is large, then it means that it's favoring the products. It's going towards completion. Okay, now how do you interpret these Ka and Kb values? Suppose you have a set of Ka numbers which all are in the same ballpark region, all right? So they all 10 to the negative 4, okay? So which of these is stronger? Look at the coefficients. The larger the coefficients among this list, the large coefficient is the one which is stronger, all right? So nitrous acid, which is 4.5 times 10 power negative 4, is the stronger among HNO2, HF, and formic acid, all right? Okay, so the coefficients are determining which of them is stronger. Same thing with methylamine and carbonate. Methylamine is the stronger base. And we'll stop here.